afternoon session. Also, in the morning, we have seen the brighter side of Gibbs sampling, and then now we'll now come to the darker side of, I guess, the slow mixer. We'll tell us about slow mixing, and Alex, please start.
So this is like Tiago's talk, but exponentially slower. But feel free to ask at any time. So yeah, we're going to try to understand the roots of slow mixing in Gibbs states. Try to get maybe a bit more understanding than something like Giger would naively give you. And yeah, so the setting is going to be what we've been looking at the whole time. So we're going to look at Lindbladian dynamics. So the idea is that for kind of any initial state sigma naught, we want to approach, as t goes to infinity, the Gibbs state. The assumptions that we'll have on the Lindbladian are a bit looser than you've seen today. We're not going to need detailed balance, in fact. But this will still give us pretty good lower bounds. So I'm going to assume that, first, right now it's written in a kind of continuous way. I'm going to make it discrete for much of the talk. So you should think of a discrete Gibbs sampler that's the CPTP map that looks something like the continuous time dynamics for a short time. It just turns out this is easier to work with in most proofs. And then when you take this, you can like truncate it. And when you do it many times, you have a tail for the exponential. Like this is all very easy to handle. So we'll usually work with a discrete case. The assumptions we'll have are that this has a fixed point at the Gibbs state. That maybe it is quasi-local. So what I mean there is that if you look at the Krauss decomposition of the channel, this is well approximated up to error epsilon for log 1 over epsilon local Krauss operators. We're imagining that we're on a lattice. So this is what you would get from Lieb-Robinson bounds. And then the third property that we'll sometimes use is that it's Davies-like. So we saw the Davies generator somewhat in earlier talks today. What I mean here by Davies-like is something very, very specific. And it's something satisfied by, for instance, the Gibbs samplers that Anthony and Andras have worked on. So I just mean that it's a constant degree. So I guess that each ki in this decomposition. Can you see if I write this low, or is this too low? It's good. Okay. Each ki is order 1 degree in like the operators that we saw that were time evolved operators. So in A nu A equal to okay, so what you should imagine is you have a set of operators, A, that are like single qubit Pallies. You have a Hamiltonian whose eigenstates are psi I vectors. And you construct these operators that are based on summing these guys over all eigenstates whose energy difference is equal to some quantity nu. So if your Davies generator is a constant degree polynomial or approximately constant degree polynomial in this will give us like some nice sense of locality for the object. So that's kind of the setting.
Do you need detailed bands?
No, I don't need detailed balance for this.
Oh.
Yeah.
What is the polynomial? Sorry.
Each Krauss operator is a constant degree polynomial in these guys.
Constant total degree or constant degree in each variable?
Total. So yeah, like I can take any your lim dot operators are approximately looking like this guy.
I guess you can sum over different nums, right? That's
Yeah, you can sum over different.
Wait, and so the K's are local, right? They're log 1 reps on local, but each A, B is probably like
So this all depends on your Hamiltonian. For some Hamiltonians, we will only have the Davies-like property, and we won't have quasi-locality.
it's easy.
Honestly,
They're both the same.
yeah. For some Hamiltonians, like we'll only care about quasi-locality and not actually need the Davies-like property. So in classical proofs of slow mixing, usually what you need is like you make local steps that are small in Hamming distance, and you have a fixed point. And that's all you need for many classical proofs of slow mixing. So here we're going to be replacing that idea of small Hamming distance with one of these two notions of locality. It's kind of the idea here.
Does detailed bands ever help you in this setting? Like, so you say here you say you don't need detailed bands, but like if having detailed bands help you?
It probably can help, but at like this, you know, for many models you don't actually need it.
Oh, okay.
So, okay. This is just kind of the assumptions we're dealing with today. But what I really want to talk about is what are the properties of Gibbs states that cause slow mixing for some kind of Gibbs sampler that follows these. So let's take a step back and look at classical Gibbs samplers. What properties of Gibbs distributions cause slow mixing classically? And the kind of picture that you get is one that comes from statistical mechanics, where you have, let's say, in the classical setting, you have a Hamiltonian on Ising spins. So x is just going to be a vector of plus minus ones. And there is a decomposition of a Gibbs distribution, mu beta, into what are called, unfortunately, pure states, these mu i's in the classical literature. And what these look like are the mu i's are constructed from a set of pi i's that are disjoint subsets of configurations, such that I'm going to abuse notation and pretend they were projectors, that you cover all the configurations. And mu I is of some spin x is defined to be normalized the Gibbs probability on x, and then the indicator that x is in the ith set. And they must satisfy a few properties. So you should think of these mu i's as individual clusters. So this is a picture of clustering. You will, in slow mixing, have multiple clusters. So no cluster has all the support of the Gibbs measure. You have a bottleneck And here what I mean is that if you move to the boundary, you have very small support in the Gibbs distribution. So if we define the boundary of size epsilon of one of these sets to be the set of all x, these are our configurations, such that the Hamming distance is at most an epsilon and at least 1, then we want the boundary of each of these guys. Sorry. To be exponentially small. And then in the classical case, you also talk about these as pure states. So no mu I can be decomposed in the same way. So pictorially, what we did here is we said we're going to divide our space of bit strings or spin configurations into clusters, like mu1 and mu2, where everything in the solid line are bit strings belonging to mu1, and everything in the dashed line are belonging to mu2, up to the rest of the bit strings that are like exponentially unlikely here, where this is also fairly exponentially unlikely. So this has a width of like order n epsilon. And if you have this structure, you expect slow mixing for a local sampler, because in order to go from mu1 to mu2, it'll have to step into the boundary region, which has some kind of bottleneck property. I'm going to prove this sort of thing rigorously for the quantum case. It's a very, very straightforward proof, so I'll skip the classical one. And we're going to try to reproduce this picture for quantum systems that are hopefully non-commuting and fancy. So yeah, we're going to imagine that our dynamics are forcing us to step through the bottleneck using this picture.
So in that picture of distance, what's the maximum distance you can cover in one step of the chain?
Right. So here we're imagining that the range of our Gibbs sampler is less than an epsilon, so that you're always going to be forced into this suppressed boundary. Yeah.
Can you talk a bit more about this purity condition? What do you mean by
Yeah.
that?
So this is actually very powerful stuff, something that I'm interested in quite a bit, because purity basically says that you can't divide these mu i's into further clusters. And what happens in many models we know classically, for instance, if I take a random KSAT, if I change the temperature and look at the decomposition to pure clusters, it will start with only one pure cluster. And then as you cool it, it will, or as you increase the density of clauses for a KSAT.
So pure cluster would mean you just have one summon?
Yeah, exactly. And then at some certain temperature or density of clauses or something, you can like shatter into many clusters. And this causes problems not only for Gibbs samplers, but whole families of algorithms. And so that gives you like a notion of average case hardness. It's quite nice. Yeah.
Can you reiterate the definition of purity? What happens if each configuration is, each pi I is a singleton? And what goes wrong in your definition?
So you want to make each bit string a separate.
Yeah.
Right, so then you have an issue that this becomes potentially exponentially small. Like making a bottleneck is going to be quite hard, since this could be order 1.
Just in the definition of purity.
Oh, I mean that it cannot be decomposed to satisfy both of these properties.
Oh, so purity depends on your choice of that bottleneck.
Yes. So,
So a cluster is something with a high weight and a bottleneck around it.
correct.
Do you need each pi I to have bottleneck? Because like it could be like, maybe there's some very good bottlenecks, and then there's one that somehow there are lots of them that connect together in a very weak way, and then like you would still have slow mixing because those guys are, those connecting ones, they would just mix with it.
Good. So for slow mixing, what we're actually going to do is group a bunch of clusters together. And so take this drawing and redraw it. I'm going to just call this middle region some region B and put both of the boundaries in there. So for slow mixing, you only need 2 clusters, basically. So you don't actually need to satisfy the purity condition.
I guess you only need one cluster, right?
One bottleneck. You need 2 clusters that have fairly large support in the Gibbs measure, so that you'll want to go to another one.
I thought bottleneck is defined for one cluster, so then don't you just need one?
Oh, but I also wanted no cluster to be all the Gibbs
I
measure.
see. Okay.
Yeah.
Is there a reason you're considering this kind of a setup? Like if you wanted to do slow mixing classically, have 2 clusters and inductance being small.
Right. So the reason I have this setup is because I'm going to write down a condition that looks similar to this in the quantum case. Because we expect that to be generically true for quantum Gibbs states, in the same way that this is kind of generically true for classical systems. Yeah.
Maybe something else I'm confused about is the formula for mu I of x suggests that each mu I of x is supported on pi I only, right?
Correct. Correct.
But then how do you have any weight on the bottlenecks at all?
Oh, so in the original picture, the not this one, but the above one, pi i's cover the entire set of bit strings. And so mu1 covers like half of the bottleneck, mu2 covers the other half of the bottleneck, so that their boundaries are in the bottleneck. But we're going to do the simpler picture that was mentioned earlier, where we just separate the bottleneck as a separate projector.
So is it clear that for any chain you always have such a decomposition, as in you start with the smallest cut and you keep going, and but it'll stay consistent?
So it's not clear that you're asking can I always decompose any Gibbs state in this form?
Yeah.
That's very non-trivial. So in many disordered systems, for example, this is what spin glass theory gives you, is a decomposition for this. If you want to show that something is average case hard, usually you have to prove such a decomposition. And so this is going to be our starting point. We're going to say for any system that you can prove such a decomposition, we like to, proving the decomposition can be easy or hard depending on your system. Okay.
So here you focus on the Hamming distances because you assume all algorithms you consider just makes local moves on the lattice.
Right. So in the classical case, it's Hamming distance. In the quantum case, we can't use Hamming distance, and we'll need to, here we know the eigenstates, so we know exactly what the distance is. We know exactly how to make projectors. The tricky thing in the quantum case will be, well, how do we produce projectors pi I? How do we measure the distance between them? Yeah.
Right. So in other words, when you said no algorithm can do, really no algorithms that makes local moves.
Yeah.
Right? Otherwise, the distance is not defined by Hamming distance, but defined by the algorithm.
Correct.
That distance induced by the algorithm.
Exactly. Okay.
Is it essential to have distance n epsilon? What about distance square root n or something?
Oh, epsilon here does not have to be independent of n. Epsilon here can be a function of n. Okay. So let's go to basically Linden's question of what are the notions of distance, or how do you construct your projectors in this setting? So I'm going to show the following theorem for the quantum case. It's a super elementary theorem. The technical meat really comes in trying to show the assumptions of the theorem are true for your particular model. This is going to be theorem on slow mixing. And it's going to be one that we showed in, it was in a paper by David Gamarnik, Bobek Kiani, and myself. And there's also a similar theorem by Tibor Rakowski, Benjamin Plack, Nico, and Vedeka Kapeni that came out basically at the same time. This is going to be our version of the theorem. There's slightly different assumptions, but it's more or less the same story. So if you have a T discrete Gibbs sampler, so imagine like e to the delta L, and you have orthogonal projectors that sum to the identity, then they need to satisfy a few conditions. One is a fixed point. Another condition is going to be some sense of locality. So this will be where we use our notion of distance. We're also going to need so we also need a bottleneck, right? And then the last thing is we're going to need a condition similar to this. So a clustering condition. So this says that we can, roughly speaking, as Anand said, like these are just, each mu I is supported only on the states in pi I. Here, we need to show that our Gibbs state has a similar decomposition. And then that gives you a slow mixing result.
Is it true that you can actually wiggle a lot of these things? Like you can, maybe they're not actually projectors. They're like both projectors, and like A and B doesn't. They're not fully orthogonal. Like, it would still work.
It's a good question. So we always produce just fully orthogonal ABC. I think you can always wiggle like up to exponentially small things if that's how much you want to wiggle. Then yeah, that should be fine. The proof for this is extremely straightforward. I think I can go through it quickly. And the hard part is like trying to show that you satisfy some notion of locality and trying to show that you satisfy a bottleneck. In particular, it's going to be hard when we have some non-commuting Hamiltonian where we can't just read off eigenstates and put them in our projectors. But if you have like a commuting Hamiltonian, and you know your eigenstates, then the clustering condition is trivially satisfied since your projectors are made out of eigenstates, everything just holds. So yeah, it's most interesting in the non-commuting case. There are in general very few results on mixing times in non-commuting Hamiltonians, but this will give us something that we can say about it.
Wait, so they don't have to be diagonal in the energy base?
No.
Almost.
Almost. I guess
it has to be almost.
Columbus clustering almost say. Okay.
Yeah.
Couldn't you just forget this T pi beta term there because you already assumed that that trace rho beta pi beta is small pi.
Yeah, you can. Yeah. It's also maybe worth saying that like this is stronger than maybe the naive thing you'd ask for. That trace of pi a rho beta plus trace of pi c rho beta is about 1. This requires that you don't have too many cross terms in off diagonals.
What was the T plus?
Oh, sorry, that's the adjoint dagger. So if you ended up in pi c, you must have come from B or C. Okay. So yeah, the proof is very straightforward. You start in a state sigma naught. It looks like this. Mixing time is a worst case statement, so we can choose our state arbitrarily. This is what we choose it to be. And then if you want to ask about like the support in cluster C after T applications of your channel, this is now a T, not a plus or a dagger, to your initial state, we use the locality condition to say that this is something that must have come from either B or C. And you iterate this thing, so you can do it many times. We can then plug in our state sigma naught on this bit over here. I'm just going to, well, let's write it out. This is the denominator, and then and then you can just use the fact that T is CPTP, and that you have a fixed point at the thermal state to turn this into something that looks like T, and then trace of rho beta pi b over trace of rho beta pi a. And then use the clustering property to kill this term. So this is order T trace of the and if you want this to be something like trace of pi c rho beta, then you'll see that T needs to be at least the bottleneck ratio. So it's much like in the classical case where the proof is extremely simple, this is just an extremely simple proof. As I said, the hard part will be in showing that your conditions here actually hold.
So, like, I guess the only actually quantum part, because I so we take ABC to be energy-based, like energy, really diagonal. Then, like, the only quantum part is the locality assumption.
Right.
Okay.
Right.
So that's where you could have entangled.
So if you're able to make your projectors in the eigenbasis,
Yes.
then you only have to show locality. Clustering is immediate. And your bottleneck, you can use like your classical bottleneck if you have a classical Hamiltonian.
Oh, I see.
If you have a non-commuting Hamiltonian, now like all three of these need work.
I guess you also need both cluster to have large weights.
Yeah.
Okay, but I guess in some cases it could be like
It could be one of our polynomial instead of
right.
cluster.
Okay.
yeah, I guess fundamentally, I think why this is so interesting to understand is because usually, like, there are tools in physics to get you into something like a pure state decomposition, even for a quantum system. And so understanding what you need to get a kind of abstraction and decompose things into pure states, I think, is a fairly fundamental thing to study. Yeah. So let's do an example, or let's try to understand maybe like the locality point. So if you have a Davies-like Lindbladian, how can you define locality? Well, our Davies-Lindbladian is constant local in these things. So we'll define the distance between two states as the minimum distance, or minimum d, such that if I were to go from one state to another, choosing different a's and nus, I can get a non-zero transition. So this should work between any two states. So we can also do this between any two subspaces. In particular, if the distance between pi a and pi c, which is just optimizing over your choices of phi's in these subspaces, is larger than the degree of L. So for something like Anthony Nonrich's algorithm, it'd be like 2. Then you have this property. So this is very easy to use if you have good control over this distance. Again, this is only easy for something like a commuting Hamiltonian. So as an example, a very trivial example would be like a classical Hamiltonian. So you might ask, well, I can maybe put some Paulis that are this AA that are like jumping, and they're not just classical x's for my Hamiltonian diagonal in Z. Like maybe I could potentially get some kind of mixing time improvement. But you can see almost immediately here the answer is no. So for a classical Hamiltonian, if I were to evaluate between eigenstates, eigenstates are going to be just bit strings. AA is just going to be a single qubit Pauli. This is only non-zero if the bit strings are Hamming distance 1 disagreeing on qubit A. You can just get that any slow mixing H classically mixes slowly quantumly as well, just by using this notion of distance. So this tells you for something like, I don't know, a random KSAT, the quantum Gibbs samplers shouldn't buy you anything.
You're starting with this state.
If you're starting with this state. Yeah, this is all like a mixing time about worst case initialization. But even classically understanding like starting from some other state is often much harder. So now the thing that I hope to tell you about is a non-commuting Hamiltonian. So we're going to look at the 2D Ising model with a transverse field. And now it's much harder. Like we don't know what the eigenstates are, so we can't just produce pi a and pi c that are diagonal in the eigenbasis. So we can't maybe tell how we should show things like the bottleneck. And then we also have to control the locality of the thing, which fortunately will be easy using quasi-locality. So what is the notion of distance we need here? It's just going to be based on the locality. So we can just say that for pi a, pi b, pi c, diagonal in the z basis, the distance between pi a, pi c is equal to the Hamming distance between them. And then the range measured under this distance of the Lagrangian is just like the number of non-trivially acted upon things. So it's like log 1 over epsilon on this 2D lattice up to some epsilon error that you can control. So this is a very easy way to get around the locality thing. Now, how do you do the bottleneck? So here, I might comment that there are few, like we need to show both the bottleneck and the clustering for pi a, pi b, pi c. In general, I mentioned that this clustering thing is much stronger than like asking for trace pi a rho beta plus trace pi c rho beta is about 1. But we can actually prove that that implies this form of clustering if you're on a dimension greater than or equal to 3 lattice by using like matrix inequalities until you get sick of it. But in 2 dimensions, the constants don't work out in the proof. And so showing this directly is like an additional task that you need for the 2D Ising model in particular. I don't know if that's any kind of deep physical fact that the proof that like a weaker version of clustering implies this in dimensions greater than or equal to 3. But that is maybe an interesting thing. And the kind of tool that we use to show the, if you construct your projectors based on the classical Hamiltonian, so if I take out the transverse field, you can use like a standard fault line argument to show slow mixing of the 2D Ising model. I want to construct those projectors here, but now turn on a transverse field. How do I compute things like trace of rho beta pi b? That's going to use something called the Poisson-Feynman-Katz representation, which is also known as just a path integral or quantum Monte Carlo. I was told by Tiago that this should be like extremely pedagogical talk, so I'll tell you how it works. Yeah.
Say what value beta to get slow support for the 2D transverse field.
Yeah, so, well, what value of beta or what value of h? I guess the one that I remember is that like as beta goes to infinity, h goes to 1 for us. But we have, yeah, there's some trade-off. But at constant beta, we get slow mixing for some h. It reproduces exactly the classical, like when you take out the transverse field, it's exactly the classical beta that you get slow mixing for, since it's the same proof.
And you also get slow mixing in 3D?
Yeah, in 3D, it's actually easier to work with things because you don't have to do this. Yeah. You can also do, for instance, for commuting Hamiltonians, you can look at LTPC codes, and they also mix slowly. There you have very good control over the eigenstates, so it's also straightforward. In Nico's paper, they use another trick to get non-commuting Hamiltonians to work, which is by adding like the Hastings trick, where you have local topological order and still mix slowly. Yeah. But for like an algorithm's viewpoint of we have a particular Lagrangian, does it mix slowly? Controlling non-commuting Hamiltonians is a bit hard unless you have good Lie-Robinson bounds, because you don't really know what happens to things. And so this is why we're stuck on a lattice over here. So I'll tell you quickly how this works. So if you have, the idea is quite nice. Let's take our Hamiltonian and divide it into two pieces and just add the identity. So we're going to have one piece that starts out as just the diagonal in Z. We're going to have another piece that's just the X piece. But then we're going to add and subtract the identity on these so that this guy over here has off-diagonal elements that are all negative and rows that sum to 0. So now it's the generator of a Markov process. So we can write, if you wanted to know about a matrix element in the computational basis of e to the minus beta h, this is just equal to, I can trotterize this between A and B. And then I can insert bases every time. So I'm going to take this as the limit. And now I'm just going to sum over paths z0 through zk, indexed by time slices, of where z of 0 is equal to x, and z of k is equal to y, and just take a product over here of time slices that go between these. And now the beautiful thing about just having a transverse field is that when you take the limit, you just get an integral over Poisson point processes. So this is going to be like an integral over paths of let's say this has eigenvalues alpha. So this is going to be like alpha of z at time s ds, and then we're going to go over all, and then we have to condition on the path ending in the correct thing. So we have, z of 1 is equal to y, and then d omega of paths starting at x. And so now here, each z of s is equal to like z times -1 time to some Poisson point process with rate h, beta h. So now you have just an integral over paths that you have to compute. And this kind of dresses up your entire classical argument. So if you have a classical set of bottlenecks that you used over here from your 2D Ising model proof with fault lines, you now have to just evaluate all of those, but with a transverse field on them. And so computing this maybe is a bit painful, but it's like something that is an O of 1 time computation to do in order to prove these properties. I guess the clustering property remains a bit trickier, but you can do a sort of, you can play around with Holder's inequality a lot in order to get somewhere. So, okay, it's all like using fairly elementary techniques in order to get these properties. So this shows slow mixing for the 2D transverse field Ising model, which is nice, and I think also gives you a recipe kind of for any system in a transverse field, up to this Lieb-Robinson bound.
Did they use the smallness of h somewhere?
Yeah, so you don't use the smallness of h too explicitly. You need it a bit, which is why you don't get to maybe the correct h that you'd expect from like a physics computation for the 2D. Yeah, exactly. So I think the real value is like h is maybe 3 point something. I don't quite remember. So yeah, I don't know if it's like just the tightness for analysis or if there's something fundamental here. Yeah, so one thing that remains open from this is if you have an all-to-all model in a transverse field. So something like the Curie-Weiss model, you can't use this trick anymore. So if I have something like this, where I have all pairs of z's coupled, now when I do Lieb-Robinson bounds, I am not able to show locality in the same way, where I just can read off quasi-locality of the light cones. And so light cones go too quickly in order to get like a super polynomial mixing time lower bound. So I think new ideas are needed for that. So you can ask, yeah, like, is this still true when you have a transverse field on? What can be shown? Another big limitation here is that you take the classical pi A, pi B, pi C over here. If I give you a Hamiltonian that's not just something in a transverse field, then how do you know what to choose over here? So non-stochastic Hamiltonians, you lose the ability to just read off guesses for your regions, and you lose the ability to do a nice path integral that has a probabilistic interpretation. And so it's unclear how to show the conditions of the bottleneck theorem. So show locality, bottleneck, clustering. But as I discussed from the earlier thing on pure states, classically, those are kind of the correct conditions you should expect from a physics viewpoint. Yeah.
For the first question, what happens if you take away the transverse field? Like,
oh, then you have nice classical proofs of this. So yeah, there's also some constant temperature. Yeah, beta equals 1, I think. Yeah.
For the Curie-Weiss, so bottleneck is one mechanism for slow mixing, right? So, but for the Curie-Weiss, is it clear that the slow mixing is due to bottleneck?
Yeah, actually, so I think for, I believe so. I can double check, but for most of
between what and what?
Yeah, I would have to look. I think for let's say most natural Hamiltonians are ones that you would consider with like a disorder term in here. And for those, a bottleneck is the natural cause for slow mixing. And so for many examples, I think it's the right framework. So for example, if you were to take the Hamiltonian that looks like a p-spin model, over here, then you get this kind of rich phase diagram where you have one cluster that shatters into many clusters. And these clusters all correspond to pure states. Historically, the way that you show that decomposition to pure states is from like the replica trick. After that was done, people had combinatorial arguments to get there. And so, yeah, for many natural models, I need to check for Curie-Weiss, but you get bottleneck arguments, or maybe somebody knows for Curie-Weiss. Yeah.
So for 2, suppose you start with a stochastic Hamiltonian, and then you perturb, you have a very small non-stochastic like, I guess I would say in your proof, if you just start changing the x to y, for example, it breaks fully, or
Sorry, so here there's nothing perturbative about h. Like h is not a perturbatively small parameter, right? It's just I have some probabilistic process that I compute. So in the thing that you're suggesting, if I turn on like a non-stochastic term that is actually perturbatively small, then yeah, perturbation theory can show you that nothing changes. But when it's constant size, unless you have something like local topological order, it becomes
that's what I mean, like,
very not clear what to do.
You put like 0.1 y everywhere.
Yeah.
And so you're saying that wouldn't the proof doesn't hold.
Well, so if you put 0.1 y, you can't turn this into some Poisson point process.
Right, and then you would
So that's why like a new technique is needed.
Oh,
So maybe you show LTO or something like this, but generically maybe it's not clear what to do. Yeah. Yeah. Yeah, I think I'm also at time pretty much. So go ahead.
What's an example where there's slow mixing, but it's not due to a bottleneck?
So I think you can cook up examples. I'm not too sure. Yeah.
But there's not some like taxonomy of reasons for slow mixing, of which bottleneck is one example.
So at least for most models studied in physics, the cause is a bottleneck. Like you have some kind of spin glass behavior where you fracture into many pieces, you have replica symmetry breaking or something like this, and this gives you bottlenecks. Showing that rigorously is like a long setting up in question classically, and it still remains open in the quantum setting. But there are at least quantum tools you can use to show this at a non-rigorous level using, like I said, the replica trick or something like this. So yeah. we think it's the right picture, but getting there is hard.
Is entropic barrier, does entropic barrier count as a bottleneck by this definition?
Yeah, so the barrier that's here has an entropic term, right? When I look at the Gibbs measure and do this bottleneck ratio. So it's a free energy barrier, or whatever you might want to call it. So yeah.
Do you think that classically people sometimes distinguish the two types of barriers? One static barriers, one is entropic. Do you think it could be profitable to distinguish the two types?
So I think I think probably looking at the free energy barrier is the right object. Yeah. Yeah.
So the bottleneck applies for this somewhat artificially chosen two configurations.
Right. Right.
Can you say something about typical situation?
Yeah, so maybe something you would ask is like, I start in the maximally mixed state and then run the algorithm. Here, there are classically some rigorous arguments, and in the quantum setting, there are non-rigorous arguments for how to work with this. There's a Schwinger-Keldysh formalism that tells you how to evaluate the time dynamics when you start from the maximally mixed state. When you couple to a bath, which would be analogous to these Lombardian samplers. And so in those settings, we also expect that if you shatter into exponentially many clusters or into few clusters, as happens in these like spin glass models, then that should also obstruct dynamics starting from the maximum mixed state. So in that sense, the worst case thing is like a good heuristic. Obviously, there are examples where it's bad heuristic, but for most natural models, it does seem like the right thing to do again.
I guess we started 5 minutes late, so I guess technically still have 5 minutes.
Okay.
Any more questions?
Yeah.
Is the slow mixing related to the anomalous diffusion, which is very extremely slow, the diffusion time scale? Or if it is different, how do you distinguish them?
I didn't quite follow the question. Sorry, can you?
There's a phenomenon of anomalous diffusion,
Yeah.
Which takes an exponentially long time to equilibrate.
is that, so I don't know anomalous diffusion, is it coupling to a bath or is it like dynamics in a closed system?
It's a closed system, yeah.
So
my question is whether it's a related phenomenon over this thing.
I can say that usually dynamics in closed systems versus when you open and couple to a bath can have very different behavior. So something like MBL usually is a closed system thing to talk about, right? So yeah, I would be happy to talk after. I'm not sure.
Do people? This is just my shallow knowledge of the literature, but like, do people already know most of the thing about physically about TFIMs or?
Yeah, I think in the phase diagram is like well understood from a physics perspective.
Any more questions? Not that thank our slow mixer. Oh, okay. So I guess some announcement for the discussion session. So, that's going to happen in 30 minutes, and then I will invite people to write down